Okay, here's an experimental setup for a demonstration, actually, not really an experiment, but an important demonstration. So let's see, I have done this setup here. Notice that I have a thermometer attached, reading device attached to these two thermometers, one in this cold bath and one in this hot bath. The hot bath is at about, I'm going to estimate it around 72 degrees. And I want to start moving kind of fast on this because I notice the temperature is going down. So 72 degrees Celsius is what that temperature is. And notice that I've already measured the cold bath at about 6 degrees Celsius. So what I want to do is take note of the fact that I have three different water temperatures. One at 6 degrees, close to freezing, and one at room temperature, which is at about 28 degrees Celsius, and one as hot as I can get it for now, which is 72 degrees Celsius. It would be even better if I had a heating plate to put it on. Okay, so let's see, what am I going to do for my experiment? I have here some red dye, and I'm going to put one drop of food coloring into each glass. So there's one drop going into my cold bath. I'm going to also put one drop into my room temperature bath. There goes one drop going into my room temperature bath. And then here I'm going to put one drop into my hot bath, And there it goes into my hot bath. A lot of air in that bath, but it's just water. Now I want you to take a look at what's happening to the three different ones. And when you do this demonstration with kids, and I'll upload a video where the kids are in the video, but I wanted to explain this from a teacher perspective. So at the beginning I wouldn't say anything. I would just say, just tell me what you see. And students will immediately start noticing some things. Like, for example, they'll start noticing that this, the red dye, food coloring in the cold bath doesn't seem to be mixing in or moving around much. And the red dye that's in the room temperature bath is moving around. And notice that the red dye that's in the hot bath has almost completely diffused. Even in this short of a time. Again, notice how my hot temperature bath is actually decreasing. So it's better if you have a hot plate to put this on a hot plate. And I recommend getting it up to about 95 degrees Celsius, just short of boiling, and then you're going to see a really good effect. Still a pretty good effect at 70 degrees. And notice that this one right here, the ice bath definitely has something going on that's different than the other two baths. The room temperature bath, take a look at that. Now, probably it's better, let's see, hold on. If I would put something behind it, so it's easier to see, something like this, and then probably have that ready to go, something like that. And now you can see a better, well, I want to get that in the way. The idea is to let students experience this and ask them to create a theoretical model that could explain this. Why is it that in cold water we see that the food dye is seemingly kind of resting on the bottom there in a little kind of singular trail? And why at room temperature has it mixed in some but not completely? Why is that happening? Let me put a white sheet of paper behind that. I think that can help things a little better to see it. Why does it look like that? You can see that it seems to be partially mixed but not completely mixed. And then over here, when I look into the hot bath, I see much more mixing going on. All right, this is a really easy demonstration to set up and do, and it's one that can spawn a lot of discussion, especially around the atomic theory. Now, of course, what you are going to guide students to do is talk about the atomic theory, and this is indirect evidence that that particles are moving fast in this hot bath and particles are moving slow in this cold bath. I want to caution you that when students say, oh, particles are moving fast, ask them, what do you mean particles? I don't see particles here. In fact, you cannot even detect individual particles of either the red dye or the water. You just can't see them because they are they're microscopic, they're molecules. But what we are seeing is the effect of moving particles that tend to mix up the water and the dye, or in this color, the food. In this case, the food coloring. So the way that I would like to have my students think about it is, imagine if you had a pit of balls, like the kind of balls that kids go into, and it was all white balls, but then you could attach to it like a vibrating trampoline to make them start vibrating around, and then when you throw in some of the red balls would mix into the white balls, but how fast they mix would depend upon how fast those balls are vibrating. So the really fast balls, the ones that would be like attached to a really fast moving trampoline, making them jiggle up and down really furiously, would be sort of analogous to the hot water. And if the balls were attached to a really sedated or kind of subdued trampoline, vibrating not as much, then they might be analogous to the cold water bath, and in between would be the room temperature bath. Okay, so that's a way to talk about things, and a way to say that if I'm making a claim, my claim is that the atomic theory describes all matter as we know it, and also, more importantly, that temperature measures the average kinetic energy, or the movement of particles. That's a theoretical framework, and we now have indirect evidence that that's the case. And what I would say is, our observation here is consistent with the theoretical framework, so it helps to bolster it. This is evidence for our claim that temperature, that is to say, hot things move faster, the particles into the hot things are moving faster, and the particles in the cold things are moving slower. This is evidence that that claim is true. Okay, so that's it.